Good morning to all. Myself, I am Dr.S.Kalaiselvi, Assistant Professor of Mathematics, PG and Research Department of Mathematics, the Standard Fireworks Rajaratnam College for Women. Now, I am going to take the video topic on subspaces in linear algebra. Subspaces are nothing but it is a subset in a vector space. In this video, we are going to learn about what is subspace and to know its results and what are all the applications and examples of subspaces. I have to mention about the introduction of subspaces. Subspaces is nothing but a subset. The subset should be non-empty. In the set, we are defining the set as a well-defined collection of objects is called a set. All the sets must have subsets. Every set is a subset to itself and empty set is also a subset. Like in that way, a subspace is also a non-empty subset W of a vector space V, in which we are going to satisfy the conditions vector addition and scalar multiplication. In this figure, we are having the whole set as vector space V and the subset as a subspace W. It should be a subset of the given vector space V. And we have to define the examples of the vectors. First, we have to know about the vectors. In these figures, first figure an array, it is just a vector with a direction. In the next figure, we are having 2V, it is 2 as a magnitude and V as a vector, 2 is a scalar. Therefore, it is 2V. Next one is the opposite direction of the vector V, it is noted as minus V, that is the negative of V is minus 1 into V. The arrow of 0 length is a single point and it represents the 0 vector. The 0 vector is very important in the subspace because it should satisfy the conditions in the figure. We are denoting the addition of vectors. In first figure, we are having two vectors U and V as a parallelogram. We are dividing this parallelogram into two triangles, that is in the first triangle V and U are added by U plus V. In the same way, the opposite triangle U plus V, which is equal to V plus U. In the same way, in the second figure, we are having three vectors U plus V plus W. We are having one associative property, that is U plus V plus W. It is equal to when we are adding V plus W first and then we have to add the U. So, it also satisfies the vector addition condition for n number of vectors. In next slide, we have to define the example in a plane. In a plane representing the line R in the R power 3, that is R power 3 is nothing but the dimension with 3 vectors, that is x, y, z. The figure is given in the following slide. Next slide. A following a plane through the origin of R power 3 forms a subspace of R power 3. It is geometrically denoted in this figure. Let W be a plane through the origin and let U and V be any vectors in W other than the 0 vector. Then U plus V must lie in W because it is the diagonal of the parallelogram determined by U and V. And the scalar addition and scalar multiplication. First one is vector addition and the second condition is scalar multiplication. That is, in the first slide we are showing the 2V arrow. Likewise, here also K into U must lie in W for any scalar K because KU lies on a line through U. Thus, W is closed under addition and scalar multiplication. So, it is a subspace of R power 3. In next slide also we are having a line. Here also we are having a figure in next slide. In next slide we are having a line through R power 3 is also a subspace of R power 3. In fact, it is also very easy to show that in a line. Next slide. in that line we are having a line through the origin, that is we are denoting a point x1 and y1, x2 and y2. This line also passing through the origin 0, 0. This is also a subspace of R power 3. In this we are having x1, y1 as coordinate and x2, y2 as coordinate. Here we are having the vector addition as x1 plus y1 and x2 plus y2. In that way the scalar multiplication also possible in this line through line which passes through the origin R power 3. So, it is also a subspace of R power 3. Next slide. Here we are having the definition of subspaces. The subspace should satisfy the following three conditions, that is the number one is the 0 vector is in the given subspace. For example, we are having W as a subspace. In this definition, we are having H as a subspace, V as a vector space. Therefore, the 0 vector should be is in H. Therefore, it is non-empty. Then number 2, H is closed under vector addition, that is for each U and V in H, they are all in the subspace H. Then the sum is also present in the same subspace H also. That is, if U and V are in H, we have to show that U plus V is also in H. This is the second condition of subspace. Then third one is H is closed under multiplication by scalars. This is where the scalar belongs to the field F and the vector is in the subspace H. For any scalar, the condition C and U are, if the scalar is K, Ku should be is in H. So, we have to satisfy these three conditions. Number 1, 0 vector. Number 2, vector addition. Number 3, scalar multiplication. We are going to see about the examples for subspaces. First example, we are given that V1 and V2 in a vector space V, and let H is a span of V1 and V2. We have to prove that H is a subspace of V. From the definition, we know that the 0 vector should be in the subspace, and the second condition, vector addition, the third condition should be satisfied as scalar multiplication. The 0 vector, first one is the 0 vector is in H, hence 0 equal to 0 into V1 plus 0 V2, therefore 0 vector is in H. Number 2, we have to show that H is closed under vector addition. For this condition, we have to take two arbitrary vectors, that is first one is U equal to S1 V1 plus S2 V2 and W equal to T1 V1 plus T2 V2. We are already having every subspace is a vector space. We have to use the axioms U plus V equal to V plus U, that is commutative property. Then second condition is commutative, third one is associative, U plus V plus W is equal to U plus V plus W. Then we are going to use the eighth axiom as C plus D into U, which is equal to Cu plus Du. Using these three axioms, we can show that the vector addition is possible. For that, Vu plus V, first addition of U plus W, then we are getting the same as U plus W is in H. Next slide. So, vector addition is satisfied. Then, by using the axioms 7 and 9, that is C into U plus V is equal to Cu plus Cv, then C of du equal to Cd of u. We are using these two conditions for the scalar multiplication, hence Cu equal to C into S1 V1 plus S2 V2. By using 7 and 9, we are segregating the scalars as Cs1 of V1 plus Cs2 of V2, which shows that Cu is in H, hence H is closed under scalar multiplication. Therefore, in this example, we are satisfying the three conditions, that is 0 vector is in H and we are proving vector addition is possible and scalar multiplication is also possible. Hence, the given H is equal to V1 of V2. Span of V1, V2 is a subspace of the given vector space V. In this slide, first we have to remember that what are all the sets. First, R is the set of real numbers, then R power 2 is nothing but it lies in two coordinates, x coordinate and y coordinate, that is we represent the ordered pairs x1, y1, x2, y2 like that. Therefore, it represents it as set of all ordered pairs. Like that, R power 3 also set of all ordered triples, that is x, y, z, or u, v, w, or x1, y1, z1 like that. In that way, we can represent the R power n also, that is set of all n tuples. Next, another set is the continuous functions defined on the set of real number line, where the boundary is minus infinity to plus infinity. If it is defined in the closed interval, then we can represent it as C of closed interval a comma b. Then P is the set of all polynomials. Then P power n known as set of all polynomials of degree less than or equal to n. Then Mn, where capital M represent the set of matrices. Then M cross n or M comma n noted m rows and n columns. Then n comma n is known as square matrices, where rows and columns are equal in the square matrix. Next slide. For next results, we should know about the definition of intersection and union. Here we are having the definition of intersection. The definition of intersection is nothing but in the set, if we are having u and v as a set, then u intersection v is also a set in which both elements of u and v should be there in u intersection v. It is notated as u intersection v is a set where x such that x belongs to u and x belongs to v. In the same way, we are able to define the union also, that is u union v is the set of elements that are both of elements u either in u or in v. Therefore, the notation is u union v equal to x such that x belongs to u or x belongs to v. Here we have to prove one result, that using the subspace, that is if u and v are two subspaces, then we have to prove that u intersection v is also a subspace of R power n. Next slide. Subspace means we have to satisfy the three conditions, that is 0 vector and the vector addition and scalar multiplication. In that way, here also we are having the non-empty set, therefore there exists an element 0 vector. Therefore, first condition is satisfied, 0 vector is in H. Then the second condition, vector addition, by using the definition of intersection, we are having u belongs to v and v also belongs to v. Then u intersection v also belongs to the same set v, hence the scalar vector addition is also possible. Therefore, the condition 1 is satisfied. For the second condition, we have to take one scalar from the field f, then alpha into the given vector u or alpha into v are also exist in the u intersection v. Therefore, the third condition is also possible. Next, hence u intersection v is a subspace for the given two subspaces. Hence, the result is if u and v are subspaces, then their intersection is also a subspace. Next slide. Here the two conditions, second condition and third condition is also satisfied. Hence, the intersection of the subspaces is also a subspace in R power n. Here also we are having the same result in next slide. The intersection of two subspaces is a subspace. Then from first one we are knowing u and v. Here we are taking v and w are both subspaces. Here also v and w is a subspace for v1 and v2 in v intersection w. Since v1 and v2 are in v and w1 w2 are in w, we are having v1 plus v2 in v and w1 plus w2 in v. Hence the vector addition v1 plus w1 and v2 plus w2 is also satisfied. Then second one, for any scalar c is in the field f and for v1 is in v intersection w, v1 is in v and in w, we are having the scalar multiplication as cv1 is in v or cw1 in w. Therefore, cv1 is in v intersection w. From this we can conclude that v intersection w is also a subspace. Next slide. Here also we are having the next result, that is union of two subspaces is need not be a subspace. That is, from this figure we are having two lines, that is in x axis we are having one coordinate and then in y axis having we are one coordinate. These two coordinates are they are not passing through the origin. We are having x comma 0 1 point and 0 comma y as 1 point. If we are taking the union, we are not at all having the elements as in v1 and v2 or w1 and w2. Hence the vector addition condition is not satisfied. Therefore, the first condition is failed. Therefore, the union of two subspaces need not be a subspace. In the same way, we are able to prove the above result as if two subspaces is contained in one another, that is w1 is contained in w2 and w2 is contained in w1, then we are able to prove the result as the union of two subspaces. Therefore, here we are having the vector addition and scalar multiplication is also possible. Hence, the union of two subspaces is also a subspace if one is contained in other. The same result is also proved in the algebraic system groups. That is why we are having the same as in our vectors. Next slide. The union of two subspaces need not be a subspace unless one is contained in the other. If v is in v and not in w, that is v must belongs to v. V is not belongs to w and w is in w, but w does not belongs to v. Therefore, we are not able to prove either v plus w is in v or v plus w is in w. Therefore, the union of two subspaces need not be a subspace. Next slide. Here also we are having one example in the matrices. Here we are taking M2 cross 2 matrix. In this matrix we are going to prove the given matrix is a subspace. That is, we have to show that W is a subspace of the vector space M2 cross 2 with the standard operations of matrix addition and scalar multiplication. Scalar multiplication is possible only when the first matrix column is equal to the second matrix row. Then the scalar multiplication is possible. First we have to prove the matrix addition. For that we are going to take two symmetric matrices. In symmetric matrices, here we are having the definition as A transpose is equal to A. That is, when we are adding A1 plus A2, then we have to take the transpose of both the matrix. Then we are taking A1 transpose and A2 transpose. By the definition of symmetric matrix, A transpose equal to A, hence A1 transpose equal to A1, A2 transpose equal to A2. Therefore, the vector addition is possible here. Then we are taking C belongs to R as a scalar and A belongs to W as again a symmetric matrix. Here we are multiplying both the scalar and vector. Then here we are having the scalar multiplication as CA the whole transpose. Then it will be divided into C into A transpose. Then by the definition of symmetric matrix, we are having A transpose equal to A, hence CA transpose equal to CA. Hence the third condition is also met. Therefore, we are having a non-empty set and the vector condition, vector addition is also satisfied and scalar multiplication is also possible in the given subspace M2 cross 2 matrix. Therefore, W is a subspace of M2 cross 2. Next slide. In linear algebra, the subspaces are playing a very important role. That is, they are very useful in machine learning. In machine learning, we are using the symmetric matrices. Therefore, they have done a great job in the machine learning processes and also in physical applications as well as in scientific programs also. A symmetric matrix is nothing but a square matrix that is equal to its transpose matrix. Here we are having some examples for symmetric matrices. First example is that is 3 cross 3 matrix, that is B. In first row B, then B transpose, the same entries are in first column. In the second row of B, the same column is exist in B transpose. Third row in B is equal to third column of B transpose. In next slide also we are having the same matrices as 2 cross 2, 3 cross 3 and 4 cross 4 symmetric matrices. Thank you all. Thank you for watching this video. This is very useful to learn about subspaces and its applications. Thank you all.